Hey there, chemists. Today we're going to do some synthesis questions that involve some of our newer functional groups, carboxylic acid derivatives, and you'll also see we're going to bring in a lot of older reactions as well, both from earlier this semester and Orgo 1. So let's get right to it. Here we have a 4-carbon carboxylic acid and a 2-carbon epoxide. Looking at the product, we want to make a different carboxylic acid that actually has all 6 carbons in it. So let's go backwards. Most synthesis problems, I always recommend planning out a retrosynthesis first and then writing it out forward, filling in your reagents. So how do we make a carboxylic acid? You can certainly make carboxylic acids by doing oxidative cleavage of alkenes, but that's a 7-carbon molecule. I don't think I want to somehow make 7 carbons from a total of 6. So even though this works, I don't know if that's our best way to make the carboxylic acid. We learned in this unit you can make carboxylic acids from the hydrolysis of any acid derivative, the appropriate ester, acid chloride, amide, even nitrile, you name it, but that's essentially the same kind of functional group, so it's not as helpful. I'm actually going to go back to Orgo 1 and remind you that you can make carboxylic acids from the oxidation of a primary alcohol. And I really like that one because now we're at a functional group where we know a lot of ways to make that group. We can make alcohols a variety of ways. Yes, you can reduce the appropriate type of carbonyl, so I could actually get this alcohol from this acid, but that's nonsense. We want to get back to something different. Thinking about the fact that we want to make this 6-carbon piece from a mixture of 4 carbons and 2 others tells me I want to make this carbon-carbon bond right there. And you can do that with an epoxide. I'll draw a little dotted line through that carbon-carbon bond. You can do that with an epoxide and a Grignard. So if we use an organometallic that has 4 carbons in it like so, you could mix that with the epoxide and you would get the alcohol that you want. Remember, Grignards are nucleophilic at the carbon attached to the metal, so it's as if I have this kind of arrow pushing where you open the 3-membered ring and you get a new carbon-oxygen bond, or actually a new carbon-carbon bond with the OH 1 more carbon away. So now we're back to a 4-carbon building block and the epoxide that they gave us. How do we make a Grignard? That's easy. You make it from the bromide. And bromides can certainly come from HBr and an alkene, or you could PBr3 the alcohol, which we can make alcohols by reducing carboxylic acids. So we're essentially there. Let me zoom out and go back to our starting materials. That's enough retrosynthesis. Once you have a good map, let's go forward. Start by turning this carboxylic acid with lithium aluminum hydride into the primary alcohol. Then we're going to convert this into a bromide with PBr3. And then we can turn that into a Grignard with just magnesium metal. And now we'll get to what I think is the key reaction in this. We're going to treat this with the epoxide. So step 1, the epoxide, and step 2, an acidic workup. And you'll turn this 4-carbon Grignard into a 6-carbon primary alcohol where we made that new bond in that step. Remember, it's as if this carbon attacks the epoxide, 3-membered ring opens, you get 2 new carbons, oxygen is attached all the way at the end of the molecule, H plus turns that O negative into an OH. And then lastly, to make the carboxylic acid, we are going to react this with the Jones oxidation to make our primary alcohol become the carboxylic acid that we want. Jones oxidation is chromium oxide and water. And there we go, about 5 steps to get from these building blocks to the acid that we want. Okay, let's keep going. Right below it we have a bromoketone. We want to turn it into a cyclic secondary amine, really different functional group, so I've got to think about retrosynthesis for this. Amines are from our previous unit, so how do you make amines? There's lots of ways. Secondary amines and tertiary amines, I think your best bet is reductive amination, and that's imagining the carbon-nitrogen bond coming from a carbon-oxygen double bond. So if we had the appropriate ketone in this case, we could treat that with this intramolecular primary amine. Remember, that works by the amine forming a bond with the carbonyl carbon. In this case, you would get a 5-membered ring with a methyl off in the end, exactly what we want. You condense, and then you reduce the imine. Speaking of carbon count, go back and look at the starting material. This is 4 carbons, we have 5, so we need to add a carbon somewhere along the way. Epoxides are great for adding at least 2 carbons, but what if you want to add just 1 carbon? I'm thinking about things like CO2, CO, and cyanide as little building blocks. Which one of those could make an amine, specifically a primary amine? The cyanide. So let's go backwards to the nitrile. You could reduce this ketonitrile. Speaking of the ketone, it's already in our starting material, so I think we're good carrying it along the way. How do I make a nitrile? You can actually make them from bromides, and they add a carbon, so we are there with our retrosynthesis. That's enough. Let's actually map this out in a forward. Let's first turn that bromide into the appropriate nitrile. Any cyanide source will do this as an SN2. I'll just write KCN and remind myself that's an SN2. And then we want to turn that nitrile into the primary amine. Remember, the CN group is a CN triple bond, and you reduce all the pi bonds, or you can reduce all the pi bonds with just hydrogenation. You can also do this with LAH, but I don't want to do that because that's going to hit the ketone, and I want to keep the ketone. So hopefully those conditions will let us carry our ketone. This is probably going to cyclize on its own and form our intramolecular imine. I'm actually going to draw the imine in the forward sense, just to remind you how it works, or a little bit of how it works. You'll get a 5-membered ring with a new carbon-nitrogen double bond. That's how reductive amination works. So this used to be this ketone, where the nitrogen cyclizes, you lose a water. And yes, it's reversible, but if we use the appropriate reducing agent, we can turn this into our secondary amine with all single bonds. So what reducing agent do we use for this? It needs to be something that only attacks the imine, but doesn't attack the ketone. So not lithium aluminum hydride, not sodium borohydride, but either of the new reducing agents we learned about in the previous unit, such as sodium cyanoborohydride, NaBH3CN will work. There's also sodium triacetoxyborohydride, NaBHOAC3. These are milder reducing agents. They attack the imine carbon. They do not attack the ketone. And that's what we want, because otherwise we'd reduce the ketone down to an alcohol, and you'd be stuck at the amino alcohol. Okay, next up in C, we have a cyclohexene. Looks like we have a total of 8 carbons. We have this hydroxyaldehyde also with 8 carbons, and every carbon is right where we want it. So unlike the first two, we don't have to change our carbon count. We just need to modify these functional groups to get the alkene that we want in the end. Like the other two, I'm going to go backwards first and ask myself, how do I make an alkene? You can make an alkene by doing an E2 elimination of the appropriate bromide. You could do an E1 elimination of the appropriate alcohol. You could do a Wittig of the appropriate carbonyl, although I don't think that makes sense here because we want our carbons already in place. I'm going to go back to the alcohol for this one because, as I said in the previous synthesis, we know a lot about the alcohol functional group, how to make them, how to use them. So let's imagine an E1 chemistry on this alcohol. That would give you the alkene. How do you make an alcohol? You could again use Orgo 1 chemistry and do a hydration on an alkene. And this might feel a little repetitive, but you could make an alkene by doing an elimination of a, in this case, less substituted alcohol, which is exactly what we have in our starting material. We have a primary alcohol way out there on the end. So we're going to do a little back and forth, elimination, hydration, elimination. But I want just a methyl on the other side of this molecule, and I have an aldehyde. So how do I take an aldehyde and turn it into just an alkane? That's a Wolff-Kishner reduction. So we're ready to go forward. So let's turn this hydroxyaldehyde into just the alcohol, where the aldehyde has been reduced completely down to the alkane. That's a Wolff-Kishner reduction, which is hydrazine and base. We learned about that in the previous unit. And then we can eliminate this alcohol to make the alkene. We use POCl3 for that. Now I want to hydrate this back to make a tertiary alcohol. All the carbons are right where they are, not changing their location at all. How do we get this Markovnikov alcohol out of this? I'm going to use oxymercuration. So step 1, mercury ion with water. Step 2, sodium borohydride. That's an old Orgo 1 reaction. Still fair game. And then to get the alkene that we want, we could do an elimination again. E1 elimination with POCl3 should go with Zaitsev selectivity, and you'll get the alkene that you want. None of these reactions are actually from our current unit. We've got some Orgo 1 chemistry and then the Wolff-Kishner from earlier in this unit. Good reminder of older reactions. Okay, there are 3 left in this problem set. I want you to hit pause and try as much as you can of all 3 of them, thinking about your carbon count in each and various functional group transformations, and then come back and see how you did. Okay, for D, we have a 3-carbon carboxylic acid, and we want to make a 5-carbon alkane. How do we make an alkane? We actually just reminded ourselves that you can make alkanes by getting rid of aldehydes and ketones with the Wolff-Kishner. I don't have that here. I have a carboxylic acid, which certainly we could turn into something like an aldehyde, but I also need to add carbons. I need to add 2 carbons. I know we said in part A that epoxides are a great way for adding 2 carbons, but we don't want a 5-carbon straight chain, which would be like that. We want a branched 5-carbon thing. So not sure how we're going to get those carbons just yet, but I'm keeping all that in the back of my mind as we think about how to get this alkane. In addition to using the Wolff-Kishner on aldehydes and ketones, remember we said the other day in our reaction review, you can make alkanes by hydrogenation of alkenes. So if I had that alkene, we could just use H2 and palladium and get the alkane that we want. And now we're back to a functional group that we know how to make. You can make alkenes, we just did it in the previous question, by doing eliminations of alcohols. So if I had a tertiary alcohol like that, I could certainly eliminate via E1 chemistry to get the Zaitsev alkene. How do I get a tertiary alcohol? Well, last semester we learned that you can make alcohols with Grignard additions and carbonyls. So we could actually add a 1-carbon Grignard to that ketone. Or let's think about newer functional groups. What if we had a carboxylic acid derivative like an ester? If I used a 1-carbon nucleophile like a Grignard or a lithiate, remember that adds twice. So that's going to get us exactly what we want. In one step, we get the tertiary alcohol from an acid derivative, and we're starting with an acid. So that's going to be our best bet right here. So let's change this carboxylic acid into an ester. I'm just going to use the methyl ester. Doesn't matter what the ester is, because we're going to turn it into the alcohol anyway. To turn an acid into an ester, you can use the Fischer esterification. So in this case, just methanol and H+. You could also use diazomethane for this transformation. Diazomethane is that special reagent, CH2N2, specifically changes acids into methyl esters. Only methyl esters for the diazomethane reaction. You want to make any other ester, use the Fischer esterification. But in this case, they both work here. Then to turn this into our tertiary alcohol, we have to bring in a 1-carbon Grignard. Those are commercially available, so methyl Grignard. And there's an acidic workup. Remember, esters react with Grignards twice, so we get 2 new methyls, both attached to what used to be the ester carbon. We actually learned that in Orgo 1, but we were reminded of it recently when we looked at ester chemistry. And to turn that alcohol into the alkene that we drew up above, we'll do an elimination with POCl3. And then lastly, if we want the alkane, we can use hydrogenation with H2 and palladium, and there's your alkane. Okay, next up in E, we have finally just one functional group in the starting material and only one type of functional group in the product, as opposed to some of these earlier ones, which were tougher, I would argue, because you're dealing with multiple functional groups at the same time. But here we've just got one functional group. Looks like we're changing our 6 carbon count into 4. So here we need to lose 2 carbons, not gain. Some of the others had us gaining carbons. Now our strategy has to be about losing carbons. We've obviously got to open up this ring somehow, and you should be thinking about 2 ways to potentially open up this ring, either ozone to give you the aldehyde or permanganate to give you the carboxylic acid. I'm just going to take a guess that we're going to use our newer transformation here, and we're going to cut that carbon-carbon bond open and make a 6-carbon carboxylic acid. Ozone works as well, so as I'm drawing this, I'm also thinking about ozonolysis. I know we use that one more often, but we now know just as many reactions of things like acids as we did for things like just aldehydes. But how do I make this, and how do I get rid of 2 carbons? How do you truncate this and effectively lose 2 carbons? Well, to make an amine, go back to the previous unit, we actually learned that you can make amines, primary amines, from things like the Huffman and the Curtius rearrangement by truncating carboxylic acid derivatives, such as the acid chloride. If you take the diacid chloride, this also works if it's the diamide. You can remove the carbonyl completely and truncate your molecule, losing a carbon. This would be doing it twice, one on each end. And we're actually there. I know how to take an acid and turn it into an acid chloride. So I needed very little retrosynthesis for this. So let's go back to our forward and in fact use the dicarboxylic acid. Let's treat this with thionyl chloride. That'll change both of the carboxylic acids into acid chlorides. 2, 4, 6 carbons in total. And then how do you change this into an amine where you actually lose both of the carbonyl carbons? You actually strip them out. You do the Curtius rearrangement, NaN3, sodium azide, with water and heat. Really involved mechanism we learned from making amines from acid chlorides via the acyl azide, and then you get 2 primary amines in place of those carbonyls. So we turned our 1, 2, 3, 4, 5, 6 carbon molecule into a 1, 2, 3, 4 carbon molecule. And that was the key to this synthesis, just realizing that we need to use one of those newer reactions that truncates it. This is called a Curtius. I would say it's a double Curtius rearrangement. You could also use the Hoffman rearrangement. It's a very similar reaction. It simply starts with the amide instead of the acid chloride. That would be fine as well. The reagents are different. It's bromine and base, and you could certainly turn this into the amide with DCC and ammonia. That would be fine as well. Okay, last up, we've got a ketone, and we want to make a hydroxy acid. Check your carbon count. We've got 5 carbons, and we've got 1, 2, 3, 4, 5 carbons, so we're keeping all of our carbons. Just a matter of changing functional groups. How do you make a hydroxy acid or a carboxylic acid and possibly open the ring at the same time? You could do a hydrolysis of an ester, imagining that this used to be one cyclic molecule. I'm going to draw it rather bizarrely at first. It's not a word, rather bizarre. Like so. There's actually a 6-carbon ring, and you can imagine hydrolyzing the ester and turning it into the carboxylic acid. And if I redraw what that looks like, that's actually a 6-carbon ring with an oxygen and a carbonyl in it. In other words, it's a lactone. And that lactone is 1 atom larger in ring size than the ketone that we start with. You can make it in 1 step with the Baeyer-Villiger oxidation. So this, as tricky as it might look at first, is a very short synthesis. If you treat this with Baeyer-Villiger conditions, remember Baeyer-Villiger reaction with MCPBA turns ketones into esters by literally inserting an oxygen in between the carbon-carbon bonds, the overall transformation. and then we can hydrolyze this ester to the hydroxy acid, or because it's an ester, I'm actually going to use saponification conditions. So that's just base followed by acid in 2 steps. You get your carboxylic acid and your alcohol, which is exactly what we want. Check your carbon count, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We're there. Okay, shortest synthesis, but I think what's challenging about these, not just bringing together all your reactions, but recognizing what you can do to them in these transformations. There's a few more to practice on the back as we continue through this unit on acids and derivatives.